All right, good afternoon.
Afternoon.
How are people today?
Not too bad.
Eating a sandwich.
Eating a sandwich, that's a good day.
Jimmy John's.
Oh, no.
I'm
I
just eating breakfast stuff.
I love Jimmy John's, but I feel bad whenever I go there because I get like extra cheese on whatever I get. And I get their chocolate chip cookies, which are like awesome. And I know I probably shouldn't.
You know, it's funny. I feel bad every time I go there too because I feel like they only have the one selection of cheese, and I'm not a big provolone guy.
Is that what that cheese is? I was never sure. It's just like this inch thick block of white stuff that tastes like cheese, but it's good.
Because unfortunately, it's very tasteless to me.
Ah, yeah.
It's Swiss, in my opinion.
Mm-hmm.
Yeah, have you ever had like Costco provolone or like a really nice provolone that's like really potent, you know? I don't taste that in the sandwich, but it's pretty good.
I have not tried high quality provolone. I have tried high quality cheddar, and that was life altering.
Go to Tillamook. They have like a 20-year reserve.
Nice.
So yeah.
Yeah, I spent a week in Vermont biking with some friends, and we went to cheese factories there, and it was like, oh, I get it.
Yeah, that's a whole other level. I haven't had the pleasure yet. You know, it's funny. I had some guys over the other day from England, and they were saying that American cheddar, even the best American cheddar, is like the worst cheddar there.
Really?
He goes, I'm gonna get it one day, and I'm gonna bring it back over here. I was like, yeah, do it.
Awesome. Yeah, totally. Yeah, it's an experience, I'm sure. All right. Cool. Well, so that will not be on the exam. So any questions? So I want to talk about the midterm, right? And just kind of run through that, make a few comments. But the midterms were really good overall, so not too much to say there. So we'll talk about the midterm, and then go on to something new. We're going to start talking about threads and threaded programming. But any questions up front on PA4 or Swing or Eclipse or whatever?
Yeah, I got a quick question. It's mentioned in like the grading area of this to deal with illegal moves and things like that. And one of them specifically said clicking outside the field. So a quick question on that. So the way that mine is set up is I have my board is, I think, 50 pixels bigger than the actual field.
Okay.
And there's a slight offset, so it sits right in the middle. And I've accounted for that because obviously the lowest you can go is 0. You can't go any lower than 0, 0. So it doesn't really affect the left side of the board. It'll always just click the left line. But if you go to the right side, it'll put you in like C8 with the way our algorithm's set up.
Okay.
But I have it so where if someone clicks on that side and it sees, column 8 or row 8, it'll actually just make it row 7. So
Okay.
someone can click on the other side of it, and it only does that line.
Yeah, that's perfect.
Okay, I just want to make sure that wasn't going to be like something I lose points on.
So the illegal move I'm worried about is, for example, if somebody were to click outside a legal box and the game decided, okay, you took your move, I'm not going to draw a line, and then it switches to the other player's turn. Because then you can cheat, right? If you're forced to make a move that's going to cause you to lose the game, you could just click outside and basically skip your turn. And you don't want that to happen. But yeah, strictly speaking, clicking outside of the box area is totally fine as long as you do something appropriate in response to it.
Okay. So just kind of account for no cheating, basically.
Yeah, exactly.
Okay.
All right, other questions? I don't know if anybody's finished PA4 yet, but I've seen some people in office who have got the core of it completely finished, and there's still details, but or at least clicking and getting lines to draw and so on and so forth.
I turned mine in already, but I
Okay.
asked that question to make sure that I didn't have to fix a couple things.
Okay, cool. Oh yeah, no, I did see yours actually. All right, anyone else? Questions? All right. Well, let's see. Can the program draw the line at the same coordinates as the box in the appropriate adjacent box? Sure, definitely. If this is like, 50, 100, and this is like 100, 100, yeah, you can use those same coordinates for the top of this box and for the bottom of this box. In fact, I recommend you do it this way. It looks like just one line. So that's totally fine.
Yeah, I remember you said use a lot of variables. I think in my main docs program, I think there was like 25 variables.
Huh, nice.
I'm using loads of constants.
Awesome. Yeah, constants are good, right? So that if you decide, oh, I want to test this with a 2x2 board, you can just sort of change some fixed variables.
With a 9x9,
Mhm.
hard to test the end game stuff.
It is. Although you could change your initialization to set all the lines true except for box 0, 0, and then you could do a 4-click game.
I should have done that.
Let's see. Don't know why I got an error at draw line method. If the error was a compile error, that's pretty easy to track down by looking at code. If it's a runtime error, that's going to be something different. So one thing to keep in mind with drawing things in this game is that you're going to have a class. I've been calling it board, and I've been calling the class myPanel and the object board. So board is going to have a paint method that you're going to override. And inside there, you're going to do all of your drawing. So if you want to draw a line on the edge of a box, it's got to happen inside here. And even though, when you click the mouse, that's when you decide, okay, I'm going to set this line to true in this box object. And at that point, you really want that line to be drawn, but you can't call draw line at that point, right? All you can do is call repaint, which causes paint to be called. And then somewhere in here is some code that will eventually look at that box, look at that Boolean, see that it's true, figure out coordinates, and then draw the line. So it's this kind of indirect drawing that we have to keep in mind, right? We don't get to draw inside the mouse handler, for example. We get to set up things in memory and then call repaint so that repaint will draw that line along with all the other lines. So that's one difference in how we're doing this that I've seen a few people have some issues with. The other thing to keep in mind is that your board array, your array of boxes has to be constructed. Each box has to be constructed, and sometimes in your paint method, if paint gets called before you've constructed your array of boards, you can start getting null pointer exceptions. Because when you first start your program, the first things that happen include, creating a J-frame, and the thing that creates the J-frame and trying to paint that will try to paint this J-panel that's inside, and it'll do that by calling the paint method. And if this relies on an array that hasn't been constructed yet, you can get exceptions in the beginning of your program. And possibly this can impair the design window in Window Builder, so that when you switch over to the Design tab, instead of seeing your playing field, you see some sort of blank window. That might be what's going on there also. So if you're getting weird behaviors like that, that's a good thing to work on in office hours. But you can see if maybe you're doing something that's involving a null pointer somewhere.
It's funny, I asked you a question last week about one of the boxes not putting an initial in. Because I was having an issue with that. I went through freaking like 500 lines of code just to find that one curly bracket was misplaced.
Awesome.
That's the problem.
Cool.
It took forever.
Yeah, that's a hard battle to go through, but it's good that you're able to do that actually. And it's a useful realization that sometimes that's what it takes, because a lot of bugs you find pretty quickly, but sometimes it takes a lot of fine-tooth comb going through your code. So my worst bug ever was about 3 weeks of debugging, and I probably debugged it 4 or 5 hours a day for 3 weeks, and finally found the bug, and it totally changed, something about how I view programming. It was subtle and it was tiny, but it was just something I'd never thought of before, and that was painful. That was.
What was it, like just a small character, or like a statement that was wrong or something?
I had a macro, so like a C macro, and it was like define inc something like x equals, so inc x was x equals x plus 1. It wasn't an increment, because obviously I could increment, but it was something like this. It was a macro that I was using inside a program, and then when I wanted to increment some argument, I would just say, increment variable, and it would get replaced with, variable equals variable plus 1. And I was writing an emulator for a Z80 and for a Z80 based operating system, and so I didn't know anything about the code that was running on this emulated system. But somewhere in there, it had something that did this: increment variable plus plus. And that translated into something like variable plus plus equals variable plus 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 1. And it ended up incrementing my variable twice.
Yeah, wow.
And I had never considered the possibility that just passing something to a macro could have this weird side effect if it's not just a pure variable. And the only way I knew I had a bug was I was running simulated basic program on the simulated operating system on the simulated hardware platform, and it worked great, except I happened to try to make a loop to print out hex numbers from 0 to 100, and after printing out F, it printed out an H instead of a 1 0. And it's like, I had no idea, because I didn't write the operating system or the basic interpreter or anything, so all I could do was run it through my debugger, instruction by instruction. And it took 3 weeks of doing that before I got to the instruction where I saw what was supposed to happen, and something got incremented by 2 instead of 1. And then it all kind of clicked. Then I got some sleep.
So did you have to go back and just change it, like undefined, or just take that defined statement out?
Yeah, I just changed this to something else. I think I just got rid of the plus plus somewhere where it was being called, and then suddenly everything worked. But
that's crazy.
But when you find bugs, the worse they are, the harder they are to find, the bigger the light bulb that will go off when you find it. Usually. Usually.
Good learning experience, right?
Yeah. Either some conceptual re-understanding, or something that will change in your coding style, or your debugging technique or something. So it's hard, but it's often worth it in the end. All right, cool. Well, if there's no other questions, let's go over the midterm and take a look at that. Okay, yeah, definitely come by office, and we can go through it. All right, 223B. All right. So let's see. Question 1. Create a class named vector that stores x, y, and z components, each an integer for the vector. Include the following: a constructor that takes 3 arguments, a method named length that returns the sum, which is not really the length of a vector, but you know. A method named 0, which zeroes out the components, and a toString method. Let me pull up my notes on this. I don't think there were a whole lot of issues with this. Maybe a few small syntax issues. All right. Yeah. So general comment. A large part of the places where people lost points were pretty simple things in the sense of you know, just missing something from the instructions, right? So not a whole lot of sort of, you know, deep understanding issues, but lots of places where, you know, if you're asked to do something and you do something different, it ends up costing points. So I think question 1, that was the main thing. A few people forgot to write the constructor. A few people printed from inside the toString method. We don't really print inside a toString. toString just returns a string version of whatever the object is, and in this case, you know, the string version would be a pair of parentheses with the x, y, z inside, separated by commas. So no big concerns on there. All right, question 2, main method that uses scanner and string classes to read from standard in, convert the input to uppercase, and write to standard out. And I mentioned during the exam this is supposed to repeat until you hit end of file. And so you need some kind of loop. A few people didn't do that. A few of them weren't in Zoom, and so they had no way of knowing that, perhaps. But so we want a loop that reads from standard in, converts to uppercase, and writes to standard out. And, you know, a variety of ways to do that. But I'm looking for a main method, right? So public static void main. With the usual arguments. And so you have to open standard in, so use a scanner. Now if you're reading from a file, then you need to construct a file. And if you're constructing from a file and feeding that to scanner, you need to have a try-catch block in case the file can't be opened. But for standard in or system.in, in this case, you don't need a try-catch. So this should succeed and return a scanner object. And then read from standard in, convert all input to uppercase, and write to standard out. So you can read one line at a time. You could read one word at a line at a time. If you read a word at a time, though, it changes your input, right? Because if you have 20 spaces between 2 words, you'll just read those 2 words as 2 separate tokens, and you could print a space in between, but you'd be changing the input, so it's probably best to do one line at a time. So while sc.has next line, and you've got options how to do this. So if we want to do this in multiple steps, we could say something like string word equals sc.nextLine. So that pulls in, or let's call it line. That pulls in a line of text. To convert it to uppercase, you can say line dot to uppercase. That does not change line, though, right? This is a method that returns a string, which is the uppercase version of this object line. So if you just do this, you don't actually accomplish anything. This gets changed to something uppercase, and then it gets thrown away. So you need to save this. For example, line equals this, and then system out print line line, and then close your loop and close your method. And that should take care of all the requirements. But since we've got objects, right, all of this could have been done with something like this. System.out.println parentheses sc.nextLine dot to uppercase semi. And this works because, you know, sc.nextLine returns a string, and a string has a to uppercase method, and so if we call that to uppercase method, the return of that is a string, and this says, hey, let's send to standard out this string. And so that would do the same thing as that. This would be a little easier to debug maybe, but if you're, you know, trying to save characters, that's a one-line version. So, you wanted to print the string, not return it, right? You needed a loop. And one thing to just be a little careful of, and I've seen this happen in 224 sometimes, in 222, right? Remember, every time that you call next line, that reads a line of input, whether you're reading from a file or from standard in or something like that. And so I've seen things pop up in code sometimes like this. So let's say print if input is longer than 5 characters. So occasionally I'll see people try to do things like this. If sc.nextLine dot length is bigger than 5, system.out.println sc.nextLine. Right, and it's a reasonable thing to do at first look, but the problem here is that every time you call next line, you read in a new line of input. And so here you're reading a line and checking its length, and if it's bigger than 5, well, we're not printing out that line, we're saying read another line from our file and print that out. And that's not what you want, right? So how do you deal with that? Well, do your sc.nextLine, save it in a variable, and then do if variable length is bigger than 5, print variable. So that's just something to look out for. It's an easy gotcha to fall into. And I think I saw that a few times on the midterm. All right, question 3, linked list of nodes. So this is a list we're constructing. We have our class node, which has an integer field called data. Actually, it has a string field called data. I corrected that on the exam too. So class node. It's got a string field called data. It's got a node field called next. And then you wanted to write a method called differ, which takes a string and returns an int. So differ string word. So examine the list, count the number of nodes whose data value differs from the given word, and return that count as the method's value. All right. So this is a 222 exercise that we have to code in Java instead of C. So the specifics of what you have to do with a data structure will vary over time, depending on what your goal is, depending on whether the list has a sentinel node or not, depending on whether the tree is a search tree or a decision tree or whatever. But the basic framework you're going to use is always the same. And I urge you, if you have not already done this, to work through in detail on paper, for example, this question, right? How to move through a list, starting with the first node and ending with the last node. And really try to nail down for you what your procedure is for that. For example, as you move from node to node, how do you know if you're done? Do you check node.next? Do you check node? Do you check to see if it's equal to null or something else? How do you begin? Do you initialize with the first node, or with the first node.next, or with null, or with something else? And once you have a way to do that in your mind that you always go to, right, then you can tailor it to whatever the requirements of the particular problem are that you're trying to solve. So here we're given a node named first, which is the first node of the linked list, or is null if the list is empty. So first is basically our handle to the list. So I'm going to make a node. I'm going to call it temp. I'm going to set it equal to first. And this is the first node of the list. We're told there's no sentinel node. So this is the first node we want to work with. And our usual structure is, we've got this chain of nodes. And the last one points to null. So what have we done? We've set up this. We've made temp equal to this first node. And we're going to see if the word in here differs from word, and if it is, we'll increment a counter. And then we're going to move temp to be the next node, and the next node, and the next node. And at the end, the last node we're going to process, temp is going to be pointing at this node. So if we terminate our loop when temp next is null, we're going to skip this node. If we initialize temp equal to first.next, we're going to skip the first node. And if we initialize temp to first.next, or we try to do something with first.data, and first is null, we're going to throw an exception. But this is safe, right? If first is null, that's okay. This will just set temp equal to null. And so my while condition is going to be while temp is not equal to null. And so after I've processed the last node, at the bottom of my list, I'm going to set temp equal to temp next. That'll set temp equal to null. That's exactly the spot where I want to exit. Right? I don't want to do anything with this value of temp because that'll throw an exception. So, well, temp is not equal to null, so let's see if our word differs from the word we were given. So we can do this, two different ways. Temp dot data dot equals word, right? If this is true, then the word in the node matches the word that we were given. So we can say if not temp.data equals word, then we can increment some sort of count. And so let's initialize a running counter to 0. And then move down the list. So temp equals temp.next, and then when we're done, return count. And that should be a good main method. Or a good differ method. So things to keep in mind here, right? So we want this, exclamation mark in here to say that the data in the node is different from the word, right? That's the differ part. A number of people skipped that, and they just said if data equals word, let's increment the count. So you're counting the wrong condition. We could also say, if word dot equals parentheses temp dot data, either way, you've got two strings you're comparing to one another. And so each of those has an equals method. We could also say, you know, if temp.data.compare to word is not equal to 0. And compare to is like string compare in C, so that'll tell us there's a difference. So issues I saw in there. So you know, skipping the first node because we initialized to first.next. Skipping the last node, not terminating soon enough and potentially generating an exception. Not handling an empty list. Now, if you're given a list where, you know, first is null, this will set temp to null. This loop will not execute, will return count, which is 0. It'll do the right thing. But somehow you've gotta make sure your code does the right thing if the list is empty. That's always an edge case. Let's see. Right, don't forget the temp equals temp.next because that moves down the list. Still saw a few issues with logic, where for example, if you put curly brackets here and here, that no longer works, right? If your word differs from the word you were given, you increment the count and you move to the next node. But if the word happens to equal the word that you were given, you're not doing any of these statements, and you're in an infinite loop suddenly. So you can put brackets around this part, but make sure that in either case you go ahead and you move down to the next node. And then a few people try to do things like, you know, temp dot size or temp dot get, right? Temp is an object of type node. Node has exactly 2 fields and no methods, right? It's got a data field and a next field. If this was a linked list, as in, you know, a linked list of some type of thing, yeah, that class contains a size method, it contains a get method, it contains all these other methods we can use, but that's not what we have here, right? We just have a collection of nodes strung together into a linked list. So you don't get to use these nice methods. What else? A few people converted things to uppercase or checked to see if things were uppercase and so on, which had nothing to do with this question, right? So sometimes code from previous program assignments pops up in people's answers for exams. If that's happening, I would say go back and look at the programming assignment. Go back, look at the question on the exam, and make sure you understand the difference, right? Why did we convert to uppercase in PA2? Well, because we wanted to tally words, and we wanted, you know, big hello and little hello to both count the same. But that was a specific requirement for programming assignment 2. The specific requirement here is, you know, count the number of nodes whose data value is different from the word given to the method. And we don't usually just, you know, convert things to uppercase or throw away punctuation or things like that just for the heck of it, right? Unless somebody asks us to do that. So those are not, you know, sort of general techniques that we use when someone says, hey, you know, read this file and print it out. Unless they tell you to throw away digits, don't throw away digits, right? So that's just a question of understanding program specs. All right, and then question 4, try catch block. Not a lot of problems here. So this method could throw an exception, right? And because of that, it actually will not compile. You'll get a compiler saying uncaught or unhandled exception on this line, and either add a try catch block or add a keyword here saying, hey, this method can throw an exception. So you need to put in a try catch block, right? And so what I wanted you to do was just add that try catch block here, the smallest try block possible. So that if you have a problem opening the file, you just return null. And so it's really just, you know, in front of this scanner method, just say try curly bracket, sc equals new scanner, close curly bracket, catch exception, curly bracket, return null. And then if you don't go into that catch block, you'll continue flowing through. You can print this message and return SC. The other trick here is, if I put a try block around this statement exactly as it's written, SC is now defined inside that try block. It does not exist down here. Right? So we saw this when we did different things with try statements. You have to declare the scanner outside. So make a statement up here, scanner SC, and then try, and just do SC equals new scanner. Just try the constructor. All right, and then so any other problems on that? Yeah, that was pretty much straightforward for most people. All right, so question 5, short answers. So these were good. These helped give me a good feel of kind of where people are conceptually with some of these ideas. So what's the signature of a method? Basically, the signature is the thing that identifies a method versus another method. So if you said, it's the name and the types of arguments, that's plenty for the 5 points. It doesn't actually include whether it's public or private. It actually doesn't include the type of return value. It's really just the name and the types of arguments. But the concept I was after here was that it's basically, the thing that identifies one method. And the key point in Java is that it's not just the name. We can have 2 methods named, area, and one takes an integer and the other takes a float and another takes 3 integers. And those are separate methods because they have different signatures. So a signature is the combination of the method's name and the types of arguments it takes. Describe in your own words what a generic is in the context of methods and classes. So a generic is a sort of general purpose class or method that can work with more than one type of object. And so anything along those lines got you credit. But it's this idea, we encountered them with linked lists. That was our big foray into generics, right? You can make a linked list of integers or strings or rectangles or whatever. Linked list is a generic class in that it can work with different types of objects. Difference between class and object. And I think pretty much everybody came up with a really good description here. So, class is kind of the blueprint. It's the description of the thing that can be constructed, and the object is the thing you get once you've done that construction. So class could be a design for a house, an object would be an actual house. One person said class is like a platonic idea, whereas an object is something with its own existence, and that was pretty cool.
That's really deep.
Yeah, I like that one. So yeah, so classes and objects. And then what's the toString method? It's a method that can be used to return a string that represents an object, basically. And so that's pretty much it. Anything around that, I was fine with. But it's a method that's used when you want to get a string that represents an object. And there's always a default one, and we can override it and so on and so forth. All right, so any questions on any of this? All right. All right. Well, it's only a quarter of, but let's go ahead and take a 5-minute break, and then we'll come back and we will start our next topic, which is going to be threading. and dealing with multiple processes running at once. Not processes, but things like processes, having multiple executions taking place simultaneously in our Java code. So let's come back at just about 5 minutes, and we'll pick up with that. All right, welcome back. So let's talk about threads. And threads are related to the idea of multiprocessing, being able to do more than one thing at a time on your computer. And you know, we know that a typical operating system will do lots of things at the same time. So I've got 360 tasks running on my machine right now. 360 tasks that exist. 3 of them are running at this particular instant. Now only 2 of them are running. A lot of them are sleeping, right? But there's hundreds of things that are potentially taking place at the same time. And that's one thing for an operating system, right? That's what the operating system does. But sometimes when we're writing a program, inside that program we want multiple things to happen at the same time. Oh, thank you. Yay. And I'll show you a real world example of that. So we've been playing a lot of Minecraft in the house the past few weeks, and you know, I'm running a server that we can all hop onto, and you can just run the server right from the command line, and it just hangs out and does its thing. But I'm actually running it from a C program, and the C program listens to, you know, messages coming from the server and responds to them. So, for example, if a server says, you know, where am I? If a player says, where am I? The C program will notice that, and it'll send a message telling them their coordinates. And so we've got, you know, these little things in here that kind of make the game a little less stressful to play and such. And so some of you may have seen a video where I had a little Altoids box with some push buttons for clearing up the weather and setting the time to daylight. And so I extended that, and I've got this little gizmo here that you can choose what you want to do. So right now, if I click this button, it'll make the time, you know, 6 in the morning. If I click this button, it'll clear the weather. If I do this, it'll clear the weather and change the time. This will switch to creative mode immediately in case you're about to, you know, lose everything. This will go back to survival mode. This will give me an iron sword in my inventory. This will restore my health, and so on. And this is just, you know, a little Arduino processor, and basically when you click the button, it just sends a message to that same C program, and it sends a request to the server to, you know, grant the entity's health or whatever. And so what does that look like structure-wise, right? We have this C program, and it's doing the following. So get message from the server. For example, when a user says, you know, /say where am I? So it reads that message, responds to it, and then it goes back up. But I also need to read a message from a USB port that this is connected to, so that if I click this button, it knows, oh, you know, Nick wants his health restored. And so I need to do something else in here, right? I need to get a message from the USB port. Well, if I do that right here, get message from USB port, I've got a problem with my loop. Because first thing I'll do is I'll sit here and I'll wait for a message from the server. And while it's waiting, if I click the button on my little gadget here, it's not going to read that message from the USB port until it gets some sort of message from the server. And then it'll respond to that, and then it'll go ahead and get the message from the USB port. So what I really want is I want an independent loop which says get a message from USB port, respond to it, set the weather to clear or whatever, and then go back up there. I need 2 loops happening simultaneously. And until I have these 2 separate loops, I have this problem that if I do both of these reads inside a single loop, one of them will block the other potentially. And this is a motivation for threads that's going to come up in PA5. when we start trying to play our dots game across a network. And it's part of a general kind of conundrum that we run into partially with interactive programs, or programs that are interacting with something outside of themselves. And so suppose we wanted to do something like this. We want to print the word hello. We want to sleep 5 seconds. We want to go back and do this again. And that's our whole program. That's our service learning project, right? It's going to print hello every 5 seconds so that people who are bored can, listen to their computer say hello. So this is not a hard program to write, right? It's just a loop. While true, print hello, do whatever we have to do to sleep 5 seconds, go back to the top again, right? But you turn that in for your SLP and your teacher says, oh, you got to add more features to it. So you decide instead of sleeping for 5 seconds, you're going to sleep some amount of time n. And we're going to set, n equal to 5. And now if you want to say hello, every 10 seconds, you can just change your code, set n equal to 10. And now it prints out hello every 10 seconds. Well, that's a little fancier, right? But if you want to get super duper fancy, it would be really cool while this was running if the user could change what n was. So it's saying hello every 10 seconds and you decide you're bored and you want to change n equal to 1. So it says hello, 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 hello. So you could try to do something like this, right? Print hello, sleep n, get n from the user. And then go back up to the top. Well, this doesn't work the way we want anymore. And the problem here is, this will print hello, it will sleep 10 seconds, and then it will wait for me to enter a new value for n. And if I'm in C and I do an fgets, that call to fgets will not return until I've typed something and hit the enter key. And if I'm in Java and I say, if sc.hasNextInt or hasNextLine, it will not return from that until I type something in and hit enter. And this is something called a blocking read, or a blocking input operation. And it's blocking in the sense that when I say, read a line of input from the user, nothing happens after that until the user provides some input. And then I come back from this functional call and I can go on. So if I had a different version of fgets, which was non-blocking, I could do something like say, hey, if there's any input available from the user, go ahead and read it. If not, come back right away. Don't wait around for it, right? Then I could do a non-blocking read right here, and I could continue my loop. And if the person hadn't typed something in, it would just go back and print hello, wait another 10 seconds. But then the next time it gets here, if the person's typed in the number 5, it would read 5, set n equal to that, print hello, and then sleep 5 seconds. So non-blocking reads are useful, but they're a little quirky. They tend to get into details that vary from one input stream to another. For example, on a Linux terminal, we can set up the terminal to be non-blocking, so that when you try to read, you can come back right away. But you have to do some things, and if your program exits at the wrong time, you can leave your terminal in a kind of weird state. And if you write a C program to do non-blocking input on Linux, and then you try to run it under a different operating system, it may or may not work. And if you try to take that same code and make it read from a network device, it may or may not work. So this non-blocking business is a little quirky. So there's a totally different way that we can do this, which would be to use a thread and create a second thread which says, get n, get input from user. set n equal to that input, and then go back up to the top. So now this loop is exactly what it was. Print hello, sleep, print hello, sleep. It just keeps doing its thing. But meanwhile, there's a separate thread, a separate process that is looking to see if the user has supplied some input. And this is a blocking read, which means, you know, when you call fgets or has next line, right, you're stuck inside that call until the person hits enter. But that does not stop this loop from executing, because this is a separate execution context. And now if the person types in, you know, 3 and hits enter, this call returns, it sets n equal to 3, and as long as this n is the same as this n, the next time this loop says sleep n, it's going to sleep 3 seconds instead of 10. And so now we've got a way for this user to control what's happening inside this loop without this loop waiting for the user to enter something.
There's also another way to do this.
Mm-hmm.
A thing called async await. And if you've ever messed with it in JavaScript or C#, it is actually the same here too. So to an extent, it's kind of expensive to spin up a thread to do something like this.
Mm-hmm.
Practicality. So there's interfaces like async await in most languages these days.
Mm-hmm.
Whatever task you want it to do, you can smush it into another thread efficiently. And you can just wait for input. Like, I've done this with sockets in C#.
Mm-hmm.
Where there's an asynchronous read method.
Mm-hmm.
And you can just have it wait on input like this.
Cool. So yeah, async is a key word here, right? Most of the coding that we've done would be considered synchronous because we're very much in control of sort of when things happen. And even if we say, you know, read something from the user, and we don't know if that's going to take 5 seconds or 5 minutes, we know that this will happen before, and whatever comes after this will happen after, and this will happen in between. And so our usual world is synchronous programming. And when we get to something like our dots game, when we put it in PA5 where 2 people are playing on different machines, we lose that synchronization. Because I might be clicking a mouse at the same time that the other player is clicking a mouse. Or I might be you know, moving my mouse while the other player is hitting the restart button. And so on and so forth. And so this makes things interesting, right? In the interesting kind of way. So we're going to look at threads. And threads are a mechanism for basically creating multiple execution streams that run more or less at the same time. And I'll just say this up front. When we talk about, you know, 2 things running at the same time, we might mean that they're actually both executing at the same instance, or we might mean that, you know, the CPU is alternating between these 2 threads, and executing a little bit of this thread, and then a little bit of that, and a little bit more of this, and a little bit more of that, and so on. It depends on the architecture of the CPU. If you have a multi-core CPU with, say, 4 cores, you can actually have 3, maybe 4 threads executing at the same time. And, you know, independent parts of the CPU hardware that are performing some operation on this thread might be doing so at the same time that other parts of the CPU hardware are executing a piece of this thread. If you have a plain old, you know, single core CPU, that doesn't happen. What happens is the operating system will execute this for a little bit and then stop, and then execute this for a little bit and then stop, and then execute this and stop, and then go back and do more of this. But we treat these the same, right? I'm just going to say, you know, 2 processes or 2 threads executing simultaneously, whichever the case is. And if you use something like the top utility, and you look at your CPU utilization, you can see I'm above 100%, right? I got 86% for Xorg. I've got my camera doing 86%. My screen recorder is doing 56%. Zoom is doing 40%. This adds up to you know, 200, 300%. That's because there's multiple cores, right? So there's 4 cores in this CPU, and this is counting how much of a core is being used by these processes effectively. So there is some, you know, actual simultaneous execution happening here. All right, so threads, right, are a way to do things at the same time, and all of this is driven by a Java class called thread. There's two ways to do threads. I'm going to talk about using this class called thread. There's also a way which we can describe as implementing a runnable, and we'll touch on that later. But I want to talk about doing this with the thread class. And so let's just write some code. And so the first version of code I'm going to write will not do anything terribly interesting. It will do something entirely mundane, something we could have done weeks ago. But then we'll make one small change to it, and it will do something very miraculous. So I'm going to create a class called myThread. And I'm going to construct an object called mt1 of type myThread. And I'm going to pass an argument to this constructor, which is just going to be an integer. And I'm going to do the following. I'm going to construct three myThreads, mt1, mt2, mt3. And in each of these constructors, I'm going to pass an integer, which this object will record so that it knows it's mt3. And this object will record this 2 that's passed to the constructor so it knows it's mt2, and so on and so forth.
I assume we have to import this as well?
Have to what?
Import it as well?
No, threads are built in. But we're going to have to write a myThread class. And that's a class we're going to construct next. So in fact, let's just go ahead and do that. So mythread.java. And I'll make a constructor, so public myThread, and it'll take an integer, which I'm going to call ID. And I'm going to make an integer variable called ID, and say this is who I am. And I'll use this funky this keyword in the constructor. So this.id equals ID means the ID up here that I'm highlighting will be set equal to the ID that I'm highlighting here. Right? So ID to the right of the equal sign means the argument. This.id means integer ID defined up here in the top of the class. So in the past, we've done this by calling this, you know, blah, and then we just say ID equals blah. But we can use this keyword and be a little fancier. All right, so we remember who we are, and now I'm going to make a method, public void run. And I'll put my brilliant comment, which says print stuff. And this is going to be a loop. It's going to do 100 print statements. So it's going to print out MT followed by the ID that I was given when I constructed, followed by a colon, followed by the value of I, followed by a space. And I'm going to do this as a print. And then I'll just print out MTID is done. All right, so pretty simple method, right? It's just going to print out 100 things side by side and then print out a done message. And so for my main method, I'm just going to run those methods mt1.run, mt2.run, mt3.run. And we know what this is going to do, right? It's going to print out a bunch of messages from mt1, a bunch of messages from mt2, and a bunch of messages from mt3. So we'll compile it, and then we'll run it, and no big surprise. So MT1 printed out the numbers 0, 1, 2, 3, 4 up through 99, and then said MT1 is done. And then MT2 printed out the numbers 0, 1, 2 up through 99, and then said it's done. And then MT3 printed 0, 1, 2 up through 99, and said it's done. And then we exited. And let me add one more message here. Let's just print out when the main method is done. And, you know, no surprise here, after MT3 says it's done, our main method is done, and the program is finished. Very synchronous. Alright, now I'm going to make one change to this. When I say mt.run, I'm going to change that to mt.start. I'm going to make two changes. I'm going to change run to start, and I'm going to, in my class, my thread, I'm going to say that extends thread. But the main change is, instead of calling run, I'm going to call start. And there's nothing in here named start, right? But this is still going to compile because I'm extending thread, and thread includes a method named start. But watch the different behavior when I run this. Alright, MT0, MT1 printed out a 0, printed out a 1, printed out a 2, a 3, did all of this up through, oh, that's not what I expected.
Is your run there an override? But that way it's automatically starting it?
Correct.
Gotcha.
So this is a little weird, but we'll work with it. Let's just see what it did, right? MT1 printed out the number 0, 1, 2, 3 up through 99, and then said MT1 is done. And then it said main method is done. And then MT2 printed a 0, but then MT3 printed a 0. And then MT2 printed a 1, MT3 printed a 1, and so on. All the way up to where MT2 printed a 99, and then it said MT2 is done. And then MT3 continued from 15, 16, 17 up through 99, and then said it was done. Now if I run this again, MT0 printed out first, followed by MT1. MT1 printed 0, 1, 2, 3, 4, 5, 6, 7, a whole bunch of output. But then somewhere MT3 started kicking in right here. And there's another MT3, and another MT3. And then MT1 printed out 99, which is the last value. And then MT3 snuck in a 7, and then thread 1 was done. And then thread 3 continued, interleaved with thread 2, and then thread 2 was done, and then thread 3 got in its last 3 outputs, and it was done. And our main method was done before any of these threads printed anything. And so this is completely asynchronous. And if I run this again, we get something totally different. MT1 and MT3 each printed out one number, and then our main method said it was done. And then 2 and 3 continued, but then 1 took over until it was done, and so on and so forth. So what's happening here? The only real change is, instead of calling run, I'm calling start. And start is not a method that we've written in here. The only method we wrote was called run. But when we call start, two things happen. So calling start does two things. One, it creates a new thread. And then it calls run. So in the thread class, there's a start method which we don't write ourselves. We use the thread method's the thread class's start method, and start does two things when you call it. First, it creates a separate new thread, and then it has that thread call the run method, which for us, we created our own run method. And so calling start makes a new thread and then calls this method down here, which does this loop of printing. But since each of these is being executed in a separate thread, they're running simultaneously, and so their outputs will appear more or less, randomly relative to the other threads. And it's worth noting again that, our main program exits very quickly. And after this, the process that was created when I said Java main, that's gone, right? That initial thread has terminated. But we have 3 other threads continuing to run. And this is what's going on inside, our PA4. We write our main program, it constructs a frame and a panel and it puts things together and so on and so forth. If you trace through that main program, if you put a print statement at the very end that says goodbye, you'll see that print statement appear really, really early, and that's it, your main program is gone. But there are other threads created that are doing things like waiting for mouse events or waiting for button clicks and so on and so forth. And so we're doing threaded programming already as soon as we're playing with swing and making GUIs and such. But we can also, work directly with threads to do whatever it is we want to do. So where might this be useful? For example, suppose you're trying to find new prime numbers. And you're just, pick an odd number, start dividing by odd numbers less than its square root, look for a factor, right? Well, I can test, 4 different numbers independent of each other. I can take a number and start looking for factors, and if I had a separate thread that was testing another number, I could be testing 2 numbers at the same time, or 3 or 4 or 25 or 100 or however many cores I have in my CPU. If I've got a GPU with 2,500 cores, theoretically I could have 2,500 threads, each doing, an independent number that is being tested for primality, or whatever I'm trying to do. This can pop up, if you're playing a game, and maybe you've got a section of your game code that checkpoints the state of the game every 30 seconds. It looks at everybody's scores and achievements and position and so on and so forth, and writes that out to a file, so that if the machine crashes, right, you haven't lost the last few hours worth of gameplay. But maybe that process of gathering that information and writing it to a file takes half a second. Well, if you do that in the middle of your main play loop, right, then every 30 seconds your game freezes for a half a second. That's really annoying, right? So what would you do? Well, you'd create a new thread and tell that thread sleep for 30 seconds, and then take a snapshot of the game state and write that out to a file. And if that takes a half second, if it takes 5 seconds, who cares, right? It's a separate execution context from the main gameplay loop. Oh, cool. Fast primes. Awesome. I'll check that out. All right. So lots of cases where we're going to use threads. The main way that we're going to bump into these is in PA5 when we're trying to deal with this idea of we're going to be doing one thing on our instance of the dots game, but the other player might be doing something in their instance. And while we're waiting for a user to make a move, we also need something that's waiting for a message to come in from the other user. For example, if they want to end the game suddenly. And so we're going to have different threads monitoring, you know, the network connection, monitoring the user input and buttons and so on and so forth. But it's going to be basically, you know, a pretty simple version of this. And I think we can get away with like creating one thread besides the main thread. I'm hoping to talk about PA5 on Thursday and Wednesday in the other section. So we'll add some specifics at that point. All right, is this making sense so far?
Yep.
So far, so good.
And yeah, this is a really interesting area to me of programming, because the debugging is a totally different experience. This is a classic situation where your code might work great 100 times, and then the 101st time it suddenly breaks. And a lot of times, you know, not a lot of times, but it's not uncommon. For example, you're developing a web-based program, maybe it's a multiplayer game or some kind of server, and you test it out pretty thoroughly and it looks like it works great, it's all going really well, right? And then the moment you go live and you put it out there on the web for other people to try, right, 5 minutes later something breaks. And why is that? Because maybe 5 minutes later you've got 1,000 people interacting with your server, and where you did your tests with 3 or 4 threads, now you've got 1,000 threads. And the chance of things happening in just the right way to expose some problem in your code has just gone up dramatically. And how do you debug that, right? If this is an occasional problem that only pops up when you have 1,000 threads running simultaneously, and it takes 5 minutes for the bug to occur, that's a really, really fun debugging challenge, right? So there's things that we'll talk about that we can do to help prevent these kinds of problems, but let's take a look at some of the issues that can come up when we're dealing with multiple executions. And so the first I'm just going to call read, modify, write. Oh, interesting. Yeah, we're going to talk about mutexes right now, actually, and semaphores or cephomores, or so let's look at a artificial example, right? But possibly a compelling one. So we're going to have a bank with some ATMs, right? Some automated teller machines for depositing and withdrawing money. And so here's a bank. And the bank has a variable called balance, which stores my current bank balance. And let's suppose my balance is $50. And there's an ATM over here. So this is a machine that has a program running inside it. And to withdraw money from the ATM, it does the following. It says, you know, B equals bank.getBalance, and then B equals B minus N. So this is to withdraw N dollars from my account. So the little program that's going to run in this machine will say, you know, get the balance from the bank. Let's call that B. Let's subtract the amount we're withdrawing from B. And then we're going to say, you know, go to the bank and set the balance to this new value B. So pretty straightforward. If I try to withdraw $10, it'll say get the balance. That's 50. B will be 50, subtract 10, B will be 40, set the balance to 40. Bingo, I got $40 in the bank. And if I get paid, I'm going to deposit N. And so how does this work? Well, get the current balance. So get the balance, increment that by n, and then set the balance. So here's the setup. I take out $10. At the same day, I win the lottery. I win $1 million, and the lottery commission deposits that into my bank because I gave them my direct deposit account because I'm an optimist. All right. So on some given day, two things are going to happen. I'm going to pull $10 out of my bank, and the lottery commission is going to deposit $1 million into my bank. And so at the end, I started with $50. I should lose $10 that I withdrew is $40, and I'm going to win $1 million. My final balance should be $1,040,040. And we can code this. This could be, a 121 program to write a withdraw function and a deposit function and, update a balance accordingly. But if this happens on, an unlucky day, here's what could occur. So these two programs are asynchronous, right? Somebody could be running this deposit program any time relative to when somebody's running this withdrawal program. And so imagine the following happens. I walk up to the ATM and I put in my card and I put in my code and I say I want to withdraw money and I say I want to withdraw $10. And now this algorithm starts running. And so the first thing it does is it says, okay, B equals get balance. So this sets B equal to 50. And then the next line of code says, B equals B minus N. Well, N is equal to 10, so it sets B equal to 50 minus 10 equals 40. Right about that same time, the person from the lottery is depositing my money. So this program starts running on a different machine. B equals get balance. Well, the balance is 50, so this sets B equal to 50. And then B equals B plus N, so now B is equal to 1,050,050. And then it says set the balance in the bank, and so the balance in the bank changes to 1,050,050. And this is done. And now this program finishes execution by executing this last step, which says set the balance equal to B. Well, what is B? B is equal to 40. So it sets the bank balance to 40, and now this program is done. And something really bad just happened, right? The deposit program ran to deposit $1 million in my account. The withdraw program ran to withdraw $10 from my account. And at the end of those programs, my bank balance is $40. I lost my $1 million. Is this a problem? It's probably a big problem.
Really big problem.
Yeah. All right. So what's the issue here? The issue is that, if I had done this whole program first and then this program, everything would be great. I'd go from 50 to 40 to 1,040,000. If I ran this program first and then this program, I'd go from 50 to 1,050,000 to 1,040,000. Everything would be fine. The problem is these two programs are running simultaneously. And this operation here, read the balance, modify the balance, write the balance, got interrupted. It did the read, it did the modify, but before it could do the write, something else came in and did a read, modify, write, And then when I did my write, I basically undid the effect of this write. And so RMW, read, modify, write. This is central to lots of things we do inside a computer. When you say I++, that's a read, modify, write. We're asking the CPU to read the current value of I, modify it by adding 1 to it, and then write it back into whatever memory location I is stored at. And we might look at this and just think of it as increment I, but it's really a read, modify, write. It's 3 things happening in sequence. And so the nomenclature is that we want these operations to be atomic. So what does atomic mean? Atom was the term that was used for if you took a mortar and pestle and started grinding sand down to finer and finer powder. Could you do that forever, or does the fineness, reach a limit at which point you can't grind it anymore? And the idea that, there was a limit to how much you could grind sand until you got down to these tiny indivisible particles, well, that was a novel idea. And these indivisible particles, we can call those atoms. And so the idea of an atomic operation is, normally you can break an instruction into smaller and smaller pieces. If I say calculate the square root of x, well, that's, one function call. But this, represents a number of steps, some loops, calculating a Taylor series or doing a Newton's method or something. And so there's for loops and there's arithmetic operations and so on. And those arithmetic operations like, I equals I plus 1, those can be broken down into smaller steps. That's what we get when we look at assembly language. We would say, move I into the accumulator register and then, increment the accumulator and then write the accumulator back into I. And sometimes those small assembly language steps can be broken into smaller pieces. When we have something like hyperthreading or a microcoded machine, those assembly language instructions might be a series of 10 or 20 lower level instructions that are being executed. But at some point, there's a sort of fundamental operation that can't be broken down any further. For example, when you tick the clock on a flip-flop, and it's a T flip-flop, and the T input is 1, and the output changes from a 0 to a 1, right? That's probably an indivisible operation. There's going to be the moment before the clock tick and the moment after the clock tick, and nothing's going to happen in between those. But most of these read, modify, writes, they are divisible. They're not atomic. And the fact that it's not an atomic operation means we have this potential for undesired interaction between 2 or more of these operations. And a way we can get around this, theoretically, is to use some sort of flag to try to make this an atomic operation. So what we'd like to know that once we start doing this, nothing else is going to mess with the balance in the bank. So as soon as we start this and we've read the balance and we've subtracted n from it, if some other process tries to read the bank balance, we want it to wait. We want to say, you can't touch the bank balance, somebody else is using it. And so we can create a flag, and these are sometimes called mutexes or maybe semaphores, and there's all kinds of terminology. Semaphore is the thing you see on railroad tracks that tell you if there's a train on the track, right? So it's a way to try to ensure exclusive use of a resource. Mutexes also do something similar. Let's look at what we could do with a flag. So our withdraw could use a global flag, which I'm going to call in use, and I'm going to say while bank in use. And I'm just going to sit there and loop. Bank in use is going to be a Boolean. It's initially false. And my deposit is going to do the same thing while bank in use. So if nobody's using the bank and I go to my ATM and I try to start a withdrawal, it's going to say, is the bank in use? No. First thing it's going to do is say, hey, set the bank in use equal to true. That gives me exclusive access to the bank balance. And now I can say b equals bank dot get balance, b equals b minus n, bank dot set balance, n, and then I can say, let's clear this flag, set bank in use equal to false. So there's my modified version for withdrawing n from my account, and here's my modified version for depositing n into my account. So while the bank is in use, I'll sit here and wait. Once the bank is free, I'll take exclusive access to it. I'll get the balance. I'll add n to it. And then I'll clear my flag. And these would probably be one routine, and you could just have a negative amount to withdraw and a positive amount to deposit, but I'm just separating them out for fun. So here's an improved version of our deposit and withdraw routines. And if I go and I start doing a withdraw, I will set this flag to true. I'll read my balance of 50. I'll subtract 10 is 40. If at that point somebody tries to deposit, they're going to sit right here because bank in use is true. And they're not going to go on and start modifying the balance in the bank until I've updated the balance in the bank to 40 and I've cleared that flag. Once I clear that flag, this will say, okay, the bank's not in use anymore. I'll take a lock on it. Now I'll read the balance. That's 40, add a million, write that in. There's my 1,000,040 in the bank. Clear the flag. Everything suddenly works. Does this make sense so far?
Yep.
And so the next question is, what's wrong with this? And there is something wrong with this.
You should set your flag outside of the while loop.
This is outside, so this is just a while. There's my whole loop right there.
Oh, okay.
Yeah.
Gotcha.
But there's one big problem with this, and it's fairly subtle. So let's replay the scenario. I'm walking up to an ATM. Person from the lottery is walking up to an ATM. We put in our cards, we put in our code. Our program starts to run. Both programs execute this statement simultaneously. They check to see if the bank is in use. Both of them get a false back. And they say, oh, the bank's not in use. Cool, I'm going to continue my program. They both come down here, set bank in use to true, and now they're both executing this code simultaneously. And we've got the same potential problem. We can read the balance, adjust it, and then this will read the balance, adjust it, write it, and then we write it, and we've lost the effect of this code.
Could you do an if statement that maybe increments a counter as somebody comes in? If that counter is more than 1?
You could do that, but here's the problem. You might both check that counter before either process has incremented it, and you might both see the counter is a 0, and then you both increment it and you suddenly see that it's a 1. So the problem here is that we're doing a read, modify, write, and this is not atomic. And if we both read a counter variable, And if it's equal to 0, we'll set it to 1, or we'll increment it and write it back. We might both read a 0, increment that 0 to a 1, we both write the 1 back, and then if we check the counter, we see it's a 1, and we think, oh, there's only one process, that must be us. And so this is another version of this reality that read, modify, write is not atomic. It can be interrupted. And our attempts to create something like a mutex, a mutual flag, that ensures, only one process accesses something at a time, inevitably involves a non-atomic read, modify, write. And kind of your only way out of this is to get some help from the operating system or the CPU or something that can do an atomic RMW. And so different systems have different ways of doing this, and we'll see a way to do this in Java that's extremely simple. We can put a keyword synchronized around something, and that will change it to basically an atomic operation. But understanding that there is a problem is the first order of business. Understanding the nature of that problem is the second order, and then we can move from there and talk about how we deal with that problem. Well, this can lead to all kinds of problems. So here's one problem where, the effect of one set of code got overridden by another set of code and I lost $1 million, right? There's other types of problems that can happen as well. So one of the most common ones is called deadlock. And an example of deadlock might be the following. Let's say I have a process that wants to read from a file and write to a printer. Right? So I want to read a file and write to printer. And let's say that on this system, only one process can access a file at a time. So your hard drive can only be accessed by one process at a time, and your printer can only be accessed by one process at a time. So think, like 1950s, where your printer was not being controlled by a server that would, take requests from a networked connection and so on. It's just a piece of hardware that you can send bits and bytes to. And if two things try to talk to the printer at the same time, you get gibberish coming out. So only one process can write to the printer, and only one process can read from the hard drive at a time. So here's process 1. And here's process 2, which is going to read a file and write to a printer. And so if both of these processes run at the same time, you've got resource contention. You've got two things writing to the file at the same time. That's chaos, right? So what can you do? You can put some sort of checks in the beginning, right? Like this. So we could say while file in use. So wait until the file's not in use anymore. And then we could say while printer in use, and wait until the printer's not in use anymore, and then go ahead and read the file and write to the printer, and then printer in use equals false, and file in use equals false. I should do this on a bigger piece of paper. All right. While file in use. So we'll sit here and we'll spin until the file is available, and once it's free, we'll set it to say, hey, the file's in use because I'm going to use it. And then we'll wait for the printer. So if it's currently in use, we'll sit here and spin. Once it's available, we'll set it to be true. Printer in use equals true to tell the rest of the world, hey, we're using the printer. And then we'll do our main loop, read file, send to printer. And then when we're done, we'll release our flags. So file in use equals false, and printer in use equals false. All right, so that's going to be our process that should hopefully play well with other processes. Let's take a look at process 2. Well, maybe process 2 was written slightly differently. First it checks to see if the printer is in use, and when it's not, it will claim exclusive access to it, and then it will check to see if it can access the file. If not, it'll sit here and spin, and then it'll say file in use equals true, and it'll go ahead and read and copy, and then at the end it will release these. All right. So this is using some kind of mutex, and we're assuming that there's some sort of, you know, atomic operation going on here, so that two things don't check to see if the file's in use at the same time. So we've cracked the mutex nut, and we've got some sort of synchronization in how we check these flags. And so we're going to assume there's no problem with, you know, things happening simultaneously. But there's still a problem here, right? So suppose process 1 begins to run. It checks to see if the file's in use. Well, nothing is in use yet. So file 1 checks this, the file's not in use, so it sets file in use to true. And at that same moment that it's doing this, process 2 begins, and it says, is the printer in use? Well, the printer's not in use yet, because this statement hasn't executed, so it claims access to the printer. Now process 1 sits here and it starts waiting for the printer to be available. Printer in use is true, so this loop's going to start looping. And process 2 is waiting for the file to be available. And file in use is true, so process 2 is waiting. And that's it. These two processes are going to sit here forever. Because the only way printer in use is going to become false is if process 2 finishes executing and sets file in use to false. And the only way file in use can move beyond this, process 2 can move beyond this spot, is if file in use becomes false. And that's not going to happen until process 1 gets down here and says file in use equals false. So basically process 1 has something process 2 needs, process 2 has something process 1 needs. And process 1's not going to release its resource until it gets the thing that process 2 has, and process 2 won't give up that thing until it gets the thing process 1 has. And your system is frozen. Both of these processes are stuck. So that's called a deadlock.
This one really is hard to find sometimes.
This one is really hard to find sometimes. And it happened in this case just because, you know, this happened to start executing in between this statement and this statement, right? If this had gotten down past this statement to where printer in use was true, and then process 2 started, process 2 would just dutifully wait here. Process 1 would finish, it would clear printer in use, this could continue, file in use would be clear, it would continue, and now process 2 is running. And if these are, you know, millions of lines of code, the chance that you're going to be at this line of code right in between these two lines of code in another process, pretty small, right? But if you have, you know, 500,000 users or 500 million users running on your server at the same time, suddenly the chances aren't so small. And so this is you know, the situation where someone says, you know, that server code you wrote, it keeps hanging up every 2 weeks or so. We come in and the whole system is frozen. And so you've got a bug that occurs once every 2 weeks and is triggered by, you know, effectively random events coming in from outside the system. So that's a deadlock situation. And yeah, so I don't know if it's particularly an object-oriented issue, but yeah, figuring out who has the key to one of these flags or mutexes can be challenging.
I've had it explained to me multiple times by engineers who've run into that problem many times,
Mm-hmm.
And I can't really fully understand it myself.
Mm-hmm.
But they usually counter with the argument that functional can be a little bit easier for concurrency sometimes.
Yeah, functional is a whole different ball game.
Yeah.
It would be fun to teach a functional programming course.
Sure would be.
All right, so that's deadlock, right? And you know, a really simple example of deadlock is you're walking down the hallway to your class, and somebody else is walking down the hallway from the same class, and you get to a point where you're standing in front of each other. Well, you can't go forward until this person gets out of your way, and this person can't get past you until you get out of their way. And you're stuck, right? You just stand there and stare at each other for the rest of eternity, because your algorithm says, you know, if somebody is in your way, just wait until your path is clear. And they've got the exact same algorithm, and so you're both stuck at that point in your code, and that's a deadlock situation. Now there's a similar concept, which is livelock. And so imagine your algorithm is a little better than this. So if path blocked, move to other side. If path clear, take a step forward. And, you know, while not at classroom. So if we start writing Java code to control our daily movements, we're in trouble. But, you know, while we're not at the classroom, I'm going to say if my path is blocked, move to the other side of the hallway. If my path is clear, take a step forward. And I'll just do that until I get to my classroom. Pretty simple algorithm. Well, the problem now is, you know, I'm walking down the hall and someone's walking down the hall, and we're both running this algorithm. And so I say if my path is blocked, I'm going to move to the other side. So I come over here. And at the same time, this other person's at the same point in their algorithm, which says if the path is blocked, move to the other side, and they come over here. And now if the path is clear, take a step forward. While it's not, so I go back to the top of my loop, and I say, hey, my path is blocked. I'm going to come back over here. And their algorithm tells them to do the same thing, and they come back over here. And now you're doing that awkward dance with a stranger where you're face-to-face with each other, and you keep moving back and forth to opposite sides of the hallway, right? And your algorithm is not stuck, right, at a line of code. You're still going through the loop again and again, but you're never getting past this while loop, right? So that's something we can call livelock. And it's you know, as deadly as deadlock, because, you know, we don't get past a certain point in our program. But it's a little different situation. Your code is still doing stuff, and it's not going to necessarily look like your entire system is frozen, and you're not moving to a new instruction, but your overall algorithm is stalled, right? And so that's.
Do you have a good example of maybe a livelock in action? I've never seen that happen.
Other than this one?
Yeah.
Like in a code?
Yeah.
Yeah, so and in fact, let's use that as a segue into the dining philosophers problem. So Dijkstra, if you did 215 and we did shortest path, or if we did it in 222, Dijkstra's algorithm for finding shortest paths through a positive weighted graph, same Dijkstra, right? So computer scientist, mathematician in the 50s, and he tackled this problem, along with a lot of other people, of how to share resources in a computer system that had multiple processes running. And so this kind of setup where, you know, two processes are trying to use a shared resource, and what happens if, you know, things just work out that they're both stuck. And so he proposed this thought exercise called the Dining Philosophers, and it's a model for resource sharing, and you'll see an analogy to a livelock in here in a minute. So here's the setup. We have 5 philosophers sitting around a table, and in the middle of the table is an infinite bowl of noodles. So there's no limit on the food supply. And philosophers like to do 2 things. They like to eat and they like to talk. And so the behavior of the philosopher is governed by the following rules. To eat, you need 2 chopsticks. You can use as long as you like. And to talk, you must put down the chopsticks. And the setup is, you know, you have 5 chopsticks on the table, because it's a cheap restaurant. And so people have to share chopsticks. And each philosopher needs 2 chopsticks in order to eat. And you can only take chopsticks that are next to you. You can't poke your fellow philosopher with a chopstick to steal their chopstick, and so on. And the question is, you know, what kind of algorithms would govern the behavior of these philosophers so that each philosopher gets to talk and eat, right? So if a philosopher never gets to eat, that's a starvation situation. So resource starvation, you need access to an object and you can't get it, right? If a philosopher starts talking but can never get around to eating, that's like a lock situation, right? So what are some of the algorithms you could use? And one simple algorithm you could start with is something like this. Step 1. Wait for the stick on the left to be free. Step 2, take the stick on the left, and then wait for stick on right, and then take the stick on the right. And then now that you have both sticks, eat for 2 minutes, and then return the stick on the left, and then return stick on the right, and then talk for 5 minutes, and then go to step 1. You're a philosopher, so you can use go-to statements. Go to stick 1 and start over again. So that's you know, possibly a reasonable sounding first stab at an algorithm. But here's the problem, right? If all 5 philosophers begin this algorithm at the same moment, well, what happens? Philosopher 1 looks to see on the left. That stick is available, so they take it. At the same time, this philosopher takes this stick, this philosopher takes this one, and so on. Now all of the philosophers are at step 3, which says wait for the stick on the right to be available. So this philosopher is waiting for this stick. It's not available. This philosopher is waiting for this stick. It's not available, and so on. And so all 5 philosophers are now stuck at step 3, and we've got a deadlock situation. So we can modify this. Wait for the stick on left, take the stick on the left, wait for the stick on the right. After 15 seconds, return stick on left, and go to step 1. Well, if the philosopher tries 15 seconds for the stick on the right and then simply returns the stick on the left and goes back to the top, they're just going to pick up the stick again. So so we could do something like this. Return the stick on the left. Wait random.
Oh yeah, you're already putting in random. That's
Yeah.
exactly right.
Wait a random amount of time and then go back to step 1. Alright, so all 5 start at the same time. They all pick up the stick on the left. Right? They wait 15 seconds, aren't able to get the stick on the right, so they each put the stick back, and now they each wait a random amount of time. Well, whichever philosopher waits the least amount of time, they're going to pick up the stick on the left, they're going to be able to get the stick on the right. And that's going to work great. The problem is, what do we mean by random? If
Random.
Yeah, so you could have each philosopher flip a coin, and if it's heads, they wait 5 seconds. If it's tails, they wait 15 seconds. Well, they could all get heads, and they could all decide to wait exactly 5 seconds, after which they're going to try to all pick up the stick on the left, succeed, and then try for the stick on the right and be deadlocked. And this is the notion that, when a computer is running and there are multiple processes that can be requesting and releasing resources, the timing of those requests are effectively random, right? But they could happen in just the wrong way where you end up deadlocking. And so even though, in most cases this should probably get us out of this conundrum, I mean, certainly if we pick a time, from 1 nanosecond to a billion nanoseconds, it's unlikely that, all 5 of those are going to pick the same random number, but it could happen. And 1 in a billion, is that unlikely? Well, I don't know. If you're Google and you've got 500 million web requests coming in every second, 1 in a billion is not very uncommon, right?
What about introducing chaos into the system at the start to make things more unlikely to step on each other? Like, maybe instead of waiting a random amount of time, you either pick a random side of a stick, or you have one person pick up 2 and the other 2 wait, and have that cascade through.
So you can find solutions like that. So the randomness really isn't a solution, because we can't assume that random guarantees difference, right? But one approach is to have something like a waiter, right? So some kind of arbitrator that assigns sticks to philosophers. And so the waiter can see, hey, this person already has the stick on their left, I'm going to let them have the stick on the right. And this philosopher hasn't picked up a stick yet, and they're going to wait. Or the waiter could randomly choose one philosopher and say, you have to put down your stick, right? And as long as your waiter is centralized, you can get out of these situations like that. The challenge there is, if you have 5 million philosophers and you have one waiter, right? That waiter is a scarce resource, and it's going to have to deal with 5 million philosophers one at a time, unless you create multiple waiters. And if you create multiple waiters, you're moving this problem into the possibility that the waiters are going to deadlock or livelock. You can find some solutions by numbering the philosophers, and if we call this philosopher 1, 2, 3, 4, 5, and we can have these philosophers work in some order based on their ID. Or we can have rules that say, if you need a stick from someone with a lower number, then the person with the lower number has to give up their stick. And that can help. It can also get into situations where one philosopher ends up eating all the time and the other one starves. Or it can get into situations where you end up serializing the behavior of these philosophers and you lose the parallelism. So a livelock analog for this might be, the same system where we had a process waiting for multiple resources, and it'll say, okay, if I can't get all the resources I want, I'm just going to release them and I'm going to wait some amount of time. Or I'm going to try, printer number 2, And if that's in use, then I'll try printer number 3. And if that's in use, then I'll release my other resources and wait a random amount of time. And that's a livelock situation where the jobs are doing things, but they're not able to complete what they're after. These will probably not come up in PA5. PA5 is going to be pretty well controlled, even though we've got 2 people on 2 machines acting independently. We're going to have a pretty good handle on whose turn it is to do something that affects the game. And so we're probably not going to run into these kinds of issues with PA5. But you'll learn a lot more about this in courses at a university. About process control, particularly process control from C, which is a whole nother can of worms. But looking at different situations where you have multiple processes that can contend with one another, and ways to deal with that, and the nuances of mutexes versus semaphores, and some of the operating system support, so P threads in C and so on and so forth. This is kind of a first intro to the subject. You will definitely see it more, and it'll be fun when you get deeper into it. But like I say, for PA5, we're probably not going to need to worry about it too much, but it's just something to be aware of, and kind of keep in the back of your mind. Multi-threading, get some experience. Yeah, so good suggestion in chat, right? And we're going to talk about sockets next week, which is how we make networked connections for PA5, for example, but also you could do something like someone suggested in chat, make a socket server that generates or tests prime numbers, right? And try having multiple threads sharing that server. And a lot of the stuff that we do, there's already good support for. So if we try to create a server socket, right, something that other processes can connect to through a network, there's already good support in there to avoid a lot of these issues. We can limit how many connections come in and create separate threads to manage each connection and so on. But theoretically, right, this is a deep subject, and for all the experience that the collective we have with programming, you still find times when something hangs up. Your PC suddenly stops responding, right? And there's a good chance it's some kind of deadlock situation, or a server hangs. And somebody has to go in and reboot it. These things still happen, and it's really difficult to 100% guarantee you have no possibility of these things occurring. But if we're aware of them, and if we use a few things to try to manage these kinds of situations, it's usually not that big a deal, unless you're Google and you're making your web page server, and suddenly you've got 1 billion hits coming in. All right, so what I want to do on Thursday is 2 things. I want to look at the Java version of all of this, and look at how we deal with preventing these kinds of situations. So there's a keyword synchronized that's very straightforward to use, and will let us do this kind of atomic locking on objects, and help us avoid some of these situations. So we'll look at some specific examples of that in code, and then I want to talk about PA5, the networked version of DOT. So those are the 2 main goals for Thursday, and then if we've got time left over, we'll go ahead and we'll start talking about networking and how we make networked connections from Java code. All right, I am 15 seconds over. That was pretty good timing. That's all I got today. Have a great afternoon. I'll see you in office hours, or I'll see you on Thursday. Thank you, everybody.
Thank you. Take care. Thanks. Have a good one.
Thanks, you too.
Okay.